Three criteria. If it's a quantity, it's specific, there's no doubt about what quantity it is, and it's got units. So that's what you should have had. All right, where's Zach Wilden? Zach, tell me about the first interval with a delta x of 1.5. What'd you put? He wants 2 to 3.5. Does it work? And what did you get for delta h for that?
1.8.
You got 1.2. Negative. What's your final answer? Negative 1.8. Okay, Lorenzo, did you find a different interval that gives that same delta t of 1.5? Where's Lorenzo? 5.5 to 8? Oh, sorry, yeah, right. 5.5 to 7. And then looking at delta h, what'd you get? Negative 1.8. Was there a question?
Yes.
Yeah, tell me.
So when you're just measuring the change,
Yep.
since you're just measuring the change, you're not measuring which way it's going, you can have a negative delta.
Yes. Yeah, we talked about that before. If the quantity increases from a lower value to a higher value, then your delta is positive. If your quantity starts at a value and ends up being a lower value, then delta will be changed negative. Yeah, so we want to put that positive and negative on the delta quantities, the delta variables, so we know that's an increase or a decrease. Good question. Okay. Lorenzo, did you get another change of 1.5? 7 to 8.5. And what did you get for the change in h? Negative 1.8. Okay. How about changes of 3? Daniel Smith. Did you get 2? Where's Daniel? Not here. Okay. What about Adam Colhase? Adam Colhase here? Adam? Yes, sir. Did you get 2 intervals that result in a delta t of 3? 5.5 to 8.5. Does it work? Did you get the corresponding delta h for that? Or can you tell me how you would find it? Is that delta h? That's your delta t, right? That's so. Sorry? Subtract 4.3 from 7.9. So which is first? What minus what? Yeah, that's opposite of what you said, actually. So you were thinking the right thing. You were thinking the right thing, you just said it backwards. You want to subtract 7.9 from 4.3. Okay, and what'd you get? You should get negative 3.6. Okay, where is Leah? You get another interval of 3? From what to what? 7 to 10. And what did you get the change in H? Negative 3.6. Okay, how about change in 5? Ali. Where's Ali? Can you tell me 2 time intervals that give a delta t of 5? 5 to 10. And? There's some 3.5 to 8.5. And what do you get for the change in H? Did you get it? Tell me. Negative 6. Agree? For both of them? Okay, easiest one. Change of 10 from 0 to 10. What's the total change in H? Negative 12. Questions on this part so far? Just changes, just understanding intervals and changes. Okay, so now we talked about constant rate of change, and we said there was kind of 3 perspectives on it. Okay, so if you don't remember what those are, you've got to memorize those. You can't apply them and understand them unless you know them first. So I'm not big into memorization in terms of like memorizing formulas and that, but these are the big ideas of constant rate of change. You've got to file those away somehow so you know exactly what those are. So looking at this table, what was one of those ideas that we said would be a perspective on constant rate of change? Yeah. Okay. We'll do that one in a second. But looking at this table, something pops out at you, right? Go ahead.
With all of them, it's always the final minus the initial.
Okay, so that's just calculating change, right? That's true. That's calculating change. But if we wanted to look at this table and quickly say, is this constant rate of change or not? What idea did we talk about? Yeah.
Equal changes in t result in constant changes in h.
Okay. Do equal t and h. So you're saying do equal changes in t result in consistent changes in h? Do they? Yeah, because every time 1.5 seconds goes by, according to our data, what happens? The flag does what? Goes down 1.8 meters, right? Goes down 1.8 meters. Negative. Every time 3 seconds goes by, it goes down 3.6. Okay, so this is that first idea of if you have the same change in x in a different place, you'll still get the same change in h. That's one perspective or kind of way to verify that you have constant rate of change. So we're saying yes or no? Yes. We're saying yes. Okay, and then he brought up another one. So what is the constant rate of change? It's per second, how many meters it goes down. So looking at this here, looking at 10 and 12. If it goes down 12 meters in 10 seconds, what calculation would you do to figure out how much it goes down every 1 second? If it goes down 12 in 10 seconds, what would you do to find out how much it goes down every 1 second? What do you want to divide? Almost, 99%. 12 divided by 10? Negative 12 divided by 10. Okay, and we would get value. Now suppose we looked at the 5 and the negative 6. If it goes down 6 meters every 5 seconds, how would you use those values to calculate how much it goes down every 1 second? What would you do? Negative 6 divided by 5. One more time. If it goes down negative 1.8 meters every 1.5 seconds, if it goes down negative 3.6 meters every 3 seconds, how would you calculate how much it goes down every 1 second? Let's try someone new here. How about Christopher Greco? Right. So you want to take that negative 3.6 meters, break it up into 3 equal pieces, which would give us how much it goes down every second. Are they all equal? And how can we represent all those ratios just in a general way? How can we represent all those ratios in a general way? Tell me what? She said delta H divided by delta T. You like it? That's it. So this was what he said. This is the second perspective. You have a constant ratio of the changes in the quantities. In this case, that constant ratio is negative 1.2. And what we said was that is the constant rate of change. That is how much every second the flag is going down 1.2 meters. Okay. So now, what about ratios of the height of the flag to the time elapsed? So what I want you to do is find some. Let's do some of that. So look at, how about h divided by t? So here's, let's do that for this row here, and say this row here. So I want you to find h divided by t for those 2 rows. Go. 30 seconds. So we got h and t. Find h divided by t, the height divided by time at those 2 times. 3.5 seconds, 7 seconds. Someone get an answer for the first one. Just shout it out. It's not 6. 2.94? Are we in agreement? Okay, so how about the other one? 0.87, I'm hearing. Are the quantities h and t, do they change together with constant rate of change? Yes or no? Do the quantities h and t change together with constant rate of change? Oh, now you changed your mind, right? Because you all just agreed with me that they did, right? So do they or not? So you just all changed your mind. Do the quantities h and t change together with constant rate of change?
Yes.
What's that? Nice and loud. And what is our check for constant rate of change? What has to be proportional, or what ratio has to be the same? Okay. If this ratio is what he's saying is, if this ratio is the same, delta H over delta T, then you have constant rate of change. And you're okay with the fact that the actual quantities H over T aren't in a constant ratio. You're okay with that? All right, so now let's pull the audience again. How many people think that the quantities H and T are in a constant rate of change relationship? What do you think? Raise your hand. How many think they're not? What are the rest of you doing? Now you don't know. Okay, well, let's leave it on the table. So before we said that didn't we say that every 1 second the flag goes down 1.2 meters?
Yeah.
Does it do that still? Is that what it's doing? So our H and T, do they change with constant rate of change? Yeah, they do. Okay. The check is not if the quantities themselves maintain a constant ratio. The check is if the changes in the quantities maintain the ratio. Really important point, right? Because you all changed your mind when you looked at those ratios. But that didn't change the fact that H and T are in a constant rate relationship because it's about the changes. The changes need to be proportional, not the quantities themselves. Are we good? Okay, and then there's one more perspective. Anyone remember what the last way of looking at constant rate of change was? Yeah, sir. Yeah, so, okay, so which is a constant multiple of what? So is H a constant multiple of T, or is delta H a constant multiple of delta T? Okay? We just proved that there's no constant multiple, right? So 3.5 times 2.94 gives 10.3. But 7 times 0.87 gives 6.1. So do we have a constant multiple? No. What about over here? If 1.5 seconds goes by, how far does it go down? 1.8. And that's because if every second it goes down 1.2, and then we got 1.5 seconds, how do we get how far it goes down? Multiply by 1.2, right? So in 10 seconds, how would you get how far the flag goes down? Times negative 1.2. Every second, the flag goes down 1.2 meters. So in 3 seconds, how far does it go down? Multiply by 1.2. Constant multiple reasoning. The change in our dependent quantity is a constant multiple of the change in t. So anybody have a question? So those are the 3 perspectives on this. Anybody have a, yes, sir?
So does that mean that you can't determine the consistency of the quantities by quantities themselves?
So what he's asking is, if you just had this table and you're just going to crunch numbers on this table, can you determine if it's a constant rate of change or not? That's what we're asking? Yeah. By making the ratios of h and t? Can that tell you if it's constant rate of change or not? No, right? Because they're not the same. The ratios aren't the same. So that, in order to analyze constant rate of change, it's all about what quantities? The changes. You gotta have this table of changes in order to start talking about, are the changes proportional? Are they in a constant ratio? Is there a constant multiple? Does an equal change in t always give a consistent change in h? Right? So those are our 3 ways to think about this. Any other questions? Okay, so let's graph this and see how this all plays out on the graph. So I can quickly here, I can highlight this. Okay, so what do we see? What am I showing you here? Which perspective am I showing you here? So those are delta t's. What about those delta t's? They're all equal, right? If we've got constant rate of change and we have equal delta t's, then what should we have? If I take equal delta t's and we have constant rate of change, where's Callaway? So if I have equal delta t's and we have constant rate of change, then what should the result be? What's that? Okay, it's linear, that's true. Where is gauge? If I have equal delta t's and I have constant rate of change, then what's the result? Where's gauge? Okay. Not sure. Okay. Tell me.
You have equal proportionate delta h's.
So the resulting delta h's will be equal to each other. Consistent change in delta h. Right? So these delta h's, if this, people talk about a line. If this thing is going down like a line, then every equal change in the x quantity will result in the same consistent change in the h quantity. Those are all the same because the delta t's were the same. Okay? What about this? What am I showing here? One second here. Okay, so I've got black and blue and red. So what was the answer?
Delta T over
What about, can we do delta H over delta T? What about delta H over delta T? The ratio stays the same. Is that what you said? So I got a delta H over delta T for the black. I got a delta H over delta T for the blue. And also for the red. And I can make that ratio. And what about that ratio? They're all equal, right? If it's constant rate of change. Okay? And then lastly, if I have, how can I, for instance, how can I find this delta H? This is the last perspective. And maybe the one we'll use the most, okay? So this is a good one. How would I calculate that delta H? How do I calculate that delta H? Yes, sir. Delta T over delta H? So delta H equals delta T over delta H. What do you think?
Delta H equals 1, like you take one quantity and subtract from another. So 1H minus another, or 1H. So.
Okay, but now we want to relate it to T, the constant rate of change. So using T, using the quantity T, how can we calculate delta H? Yes, sir. Yeah? Negative 1.2 times T. What do you think? Is that right? Delta T. Delta T. Those are different, right? Those are different. So in order to get any delta H, all we need to know is delta T, and our change in the height is always negative 1.2 times whatever the time change is. So will that be true for the blue one? Yep, and the black one also. That the amount it goes down is always 1.2 times whatever time you have. Any questions on, we're going to summarize it here in a second. Any questions on this example? So hopefully we're filling in the gaps. You were working on the web work and maybe you had some questions and you weren't sure about things. Hopefully now this is starting to come together, starting to make sense. But you want to memorize these three principles. We'll go over them again. You got to memorize these because if you don't have them at your disposal, if you don't have them as tools, you can never apply them. So you got to memorize them and understand them, and then you get a problem that doesn't say anything about changes, right? It's talking about cruise control on the highway, but you got to apply this stuff. You got to apply this stuff. Okay. Last chance. Questions on this example? Okay, so hopefully this next thing will be helpful. Constant rate of change. This is overview. Okay, so don't try to write all this down. Watch it on the video and watch it several times. Memorize these principles. Memorize them so that you can apply them. First principle, equal changes in one quantity result in consistent changes of the other. That was like in the table, right? That's the first question in the table. Change in one quantity is a constant multiple of the corresponding change in the other. Whatever change in time you had, that change in height of the flag was always negative 1.2 times that change in time. Always gave you the change in height. And then we have the constant ratio of the corresponding changes. So let's see these visually, okay? I worked hard on this, so I hope you appreciate it. Here we go. So you all said it makes a linear equation, right? It makes a linear equation. So this is the first one. Equal changes in one quantity result in, so equal changes in x will result in what? Yeah, so the changes in y themselves will be equal to each other, right? Consistent changes in y as a result. That's perspective number one. Number two, the change in one quantity is a constant multiple of the change in the other. So here's some differing changes in x. How can we calculate the change in y? How can we calculate the change in y for each one of those? It's some constant multiple times the change in x. Each one of those changes in y has an associated change in x. Multiply by that constant multiple, it will give you that change in y. So we have this statement here. Finally, what was the last one? Constant ratio. Are x and y in a constant ratio? No, okay? Or not necessarily. They might be, but for constant rate of change, that's not guaranteed. What is guaranteed is what constant ratio? Cujo, what for x and y to be in constant rate of change, what constant ratio is guaranteed? Malenko? Where's Malenko? No? Okay, how about Edward Williams? The question is, if we have constant rate of change in these quantities y and x, what constant ratio is guaranteed? The ratio of what? The delta. So tell me what the ratio is. Delta. Delta y equals delta x? The ratio of delta y to delta x, right? So for this small triangle, that ratio is the same as the ratio for the medium triangle, delta y to delta x, same as the large triangle. It's constant, and that is the value of the constant rate of change. That is how much y changes for a change in x. That's how much y changes for a unit change of x. So, like I said, watch that on the video several times. You've got to memorize those three principles. So when you come to a problem that doesn't say anything about changes, doesn't say anything about constant rate of change, you have to pull from what you need and use the tools to do it. Question? It could be, but we're saying that x is independent and y is dependent on it. So we want the rate of change of y with respect to x. So that'll be this, delta y over delta x. Okay. Another question? That's a good question. So it's a matter of kind of dependence. It's like what's independent, what do you have control over, and then the other quantity is going to be dependent on that. So if you're driving on the highway and you're looking at time and distance, what will your y be? Distance, and your x will be the time. Because speed. So now speed is the rate of change, and that's going to be change in distance divided by change in time, or delta y over delta x. Is that better?
So basically, you can say that it's miles per hour or hours per mile, but it's really depends.
Yeah, you could do the whole problem in hours per mile, but we just don't really deal with that quantity hardly at all, right? So we're speed is distance per time, so that's how we make this distance y and the speed, or the time x. Yes, sir?
Would that be the same thing as slope, like rise over run?
Yes, right. So how do you calculate slope? Good. Well, how do you calculate slope? What is it? Y over x? y2 minus y1 over x2 minus x1. Oh, but wait a second. What is y2 minus y1? That's a change in the quantity y. It's delta y. So it's the same thing, right? It's the same thing because y2 minus 1 is how much y changes from y1 to y2. Okay, but slope is just kind of a visual of it. So what's really the important thing is how they're changing together. This value, thinking of it as the constant rate of change. So slope is the visual representation. Okay, other questions? Good questions. All right, so go to, I think it's page like 23 in your workbook. It's this one. It's a candle. Is it page 23? Is that right? What is it? 20 what? 30, 33, 35? Anyone find it? Oh, sorry. Investigation 4. Module 2, Investigation 4. 35, please. 35. And what I want you to do is to make this a little easier, change the scale to 2. 2, 4, 6, 8, 10. So it looks like this. Okay? So we note that it's burning at a constant rate of 2.2 inches per hour. And after 3.5 hours, the current length or height of the candle is 8.3 inches. All right, so we have constant rate of change. They're telling us it's constant rate of change, and it's 2.2 inches per hour. So first of all, they want us to represent a change of time of 2 hours. So starting at 3.5 hours, do we draw a horizontal or vertical line to represent a change of time of 2? Right or left? So I'm going to go to the right, like this. And that is, how do we represent that? What symbol is that? Yeah, delta. Yeah, delta t, or in this, so delta x. Okay. And what does that equal? 2. Now we're going to apply one of our constant rate of change principles. We want to know the corresponding change in the length of the candle. How does that represented? Delta y. So we want to know how much burns off of this candle in those 2 hours. So how can we use one of the principles of constant rate of change to calculate that? Yes, sir? Yep, we got constant rate of change. So we got constant multiple reasoning. So we're going to take equals negative 2.2 times the change in x. What do you get? Negative 4.4. And so 1, 2, 3, 4, something around here. Okay? And so that's our delta y of negative 4.4. So using these symbols that we've got here, what we want to know now is, what's the length of the candle now? So can we set up before we actually get the number, can we set up an expression of x and y and delta x and delta y that would calculate now how much of the candle remains, how long it is? Yeah?
Insert variable here of candle length equals 8.8 minus the quantity of hours you've been burning it times 2.3.
Okay, our goal is to use x, y, delta x, and delta y. So you may, yeah, but we want to use the symbols because that's how we represent these changes. So we use the symbols. Yes, sir?
I have a question.
Yeah.
In the first column, we put delta y in the horizontal line. Now you're putting delta x in the horizontal.
Huh? This has always been delta x, right? Yeah, horizontal is always delta x, and vertical always delta y.
You switched it around.
Did I switch it around? I don't think so. Go back and watch the video. I think it's been consistent. Yeah, our x-axis is our horizontal, and so delta x's will be horizontal segments. Delta y is vertical, so delta y's will be vertical segments. Yes, sir? And that was the problem. Represent an increase in time spent 2 hours. That was the question. Yeah, that was the question. So how can we use x, y, delta x, and delta y to come up with an expression that will get us what the new length or the height of the candle is? Yes, sir?
Y equals negative 2.2 delta plus 8.3.
Okay, so what he's saying is, and this is the same thing that this gentleman here said, so the new y equals the old y, what? And what do we need to do to that? Plus, what? Well, but we got the negatives built in, right? Negatives are built into our changes. So isn't this true? The new y value will just be what the y value was before, and we're going to add on the change. And we'll get the new y. Does that make sense? So what is the old y? 8.3. And now we know the change in y. What was the change in y? Negative 4.4. Equals? And that's about where we landed here, 3.9. So 2 principles that we used. The constant multiple reasoning of constant rate of change, that changes in y will always be negative 2.2 times changes in x. And then this is kind of a new principle, but should make perfect sense, that a new y equals an old value of y plus whatever, however much it changed. Right? However much it changed. Is it good?
I think it's supposed to put you in the unit,
What's that? Yes, excellent. What are the units? Inches. It's the new length of the candle. Other questions? So we want it. So here, this is kind of really important. So I know it's Friday and it's the end of class, but where we're going next is a really important thing we want to get to. We want to use the same idea, the same kind of process, to be able to write the equation of the line, which is the result of this constant rate of change. Okay? So we're going to follow the same process again, but now, can I erase with the blue? What's up there? We're good? Actually, I don't want to yet. Right there. Okay, so we got this point. What did we say a graph was? A graph consists of points. When you draw a line, it's just a fast way to do what? Draw all the points. If we were to actually draw what it is, how long would it take us? It takes forever because we'd be sitting there making points all our lives. That's why we can draw a line really fast with a ruler or even freehand. But what we know when we do that is what we just did is we drew an infinite number of points. That's what we did. Okay, it's a little distracting, guys. Guys, it's a little distracting. Okay. So what I want to do here, it doesn't matter which one I pick. I want to represent all those points as, I can pick any one. So this one, xy, or this one down here, xy. I'm going to put it over here instead. Okay, so xy, say this one, okay? Doesn't matter, any of those, because remember, x is all the values that it can take on, and y is all the values that it can take on. So it can represent any of those. So the first thing we want to do is what we did before is, what is delta x starting at 3.5 hours? So what is, let me pick a different one because that's kind of where we were before. So let's pick this down here. So the numbers don't matter because the one I pointed at could have been any of those because we want to represent all of them. We want to represent all of them. Okay, so delta x. He wants, what do you want? 3.5 minus 2. Where's the other way around? Where's the 2 coming from? What's the x-coordinate of our initial point? What's the x-coordinate of our final point? No. This is what I've been saying for I could have picked any one of those points, and we're representing all of the points. How? With what x value? No, x. X. X represents any point that I would have picked here. It's x-coordinate. I could have picked this one. I could have picked this one. I could have picked this one. So what is the change from 3.5 to x? And how would you write that? How would you write what delta x is? 3.5 minus x. Agree with that? See, when you did it in the web work, it was so easy. You had these really easy questions where you're doing all these delta x's and said, what's your formula for finding delta x? What is it? No, it's the final value of the quantity minus the initial value. So what would delta x be? X minus 3.5. Do you see? Where x can take on any point on the line. X can be any point on the line. And we're going to start at 3.5. So we represent that this way. There's delta x equals x minus 3.5. Does it make sense? It was hard to get there, but hopefully it makes sense now. Final value of the quantity minus initial value of the quantity gives the change. Gives the change. And you did that a million times in the web work. Okay? So now we want to use what is delta y in terms of in terms of delta x. What is delta y now? No, in terms of delta x. We got to use this is the big point. Use constant rate of change reasoning.
Y minus 8.3.
In terms of delta x, use constant rate of change reasoning. Which rate of change reasoning, constant rate of change, could we get the change in one quantity? Equals what? Negative 2.2 times delta x. Okay? Which is, and we know what delta x is now, right? What is it? X minus 3.5. See that? So this now, our change in y, is negative 2.2 times the change in x, which is this right here. Are we good? Last principle was, so writing the equation of the line means we want every y. Every y, which is like our new value of y, what did we say was the old y plus the change in y. And now we've got that. There's the change in y. And we started at this point, so what was the old y? 8.3 plus, and delta y is negative 2.2 times x minus 3.5. So everything has meaning, right? Everything has meaning, and we just wrote every single point on that line. Right? This is the old y plus the change in y. And now we just represented every single point, where each point is a number of time elapsed and the current length of the candle. And that's the equation of the line. Okay? So, do you need to know this? Can I just do y equals mx plus b because I'm really good at that? Yes, you need to know this because this is about reasoning about how the quantities change together, and that's what calculus is about. All right? 2 tasks. You've got written homework for next week. You're going to hand that in recitation, either Wednesday or Friday, and then you have the next web work Wednesday before class. Be very safe this weekend, please.
Hi.
Hello.
I registered late.
Okay.
This is my first class here.
Okay.
What do you want me to do to catch up?
I'll let you know. Let me turn this off here.